Okay, welcome guys to Physics 390 class number 4. In this class, we're going to be talking about the TISE, the time-independent Schrödinger equation, the harmonic applied to the harmonic oscillator, and we're going to take an algebraic approach to solving it. And this material comes from chapter 2.3.1 of your textbook. Okay, so why interested in the harmonic oscillator? Well, you have some idea of this already. You've studied classical physics and you've seen the harmonic oscillator is very important there. So, so just to remind you, the classical harmonic oscillator has an equation of motion. F, the force, is minus kx, that's Hooke's law, is equal to m times the acceleration d squared x dt squared. So minus kx equals m d squared x dt squared. And its potential energy is V equal 1/2 kx squared. Okay, so why is it useful? Well, even systems which aren't purely classical harmonic oscillators can be approximated by classical harmonic oscillators. So if we expand a minimum of the potential at a given position, x equal x naught, for small displacements using a Taylor series, we can actually approximate it as a harmonic oscillator with a spring constant equal to the second derivative of the potential at that position x naught. So that's illustrated here. We have a potential here which is not a parabola, so not a pure harmonic oscillator potential, but it oscillates around and back and forth. And near this minimum at x equal x naught, it's pretty close at that minimum to a parabolic potential. And so we can approximate it by a Taylor series there. The constant term we can ignore because adding a constant term to a potential doesn't change the force. The first Taylor series term with the derivative is equal to 0 since it's flat at this point. So it's the second term, 1/2 times the second derivative of the potential at x naught times x minus x naught squared, which is the dominant term. There are other terms in x minus x naught cubed, but they're small compared to this one. So you see that this form 1/2 times this times displacement squared is the same as the form on the harmonic oscillator. So we have an effective k as the second derivative of v with respect to x evaluated at x naught. So harmonic motion occurs in lots of places, not just a mass on a spring, but in molecules, in vibrational motion in molecules, in interatomic potentials, in lots of places. In biological systems, there's close to harmonic forces, which we can use the harmonic oscillator for. So it's a very useful form. So a little bit more on it. You probably remember we take omega as defined equal to the square root of k over m, and that's our frequency, angular frequency for the harmonic oscillator. And so solving that for k, we get k is equal to, squaring both sides, omega squared is equal to k over m, so k equals m omega squared. And so we get v of x is equal to 1/2 kx squared, but k is m omega squared. So that's 1/2 m omega squared x squared. Okay, so that's our potential as we write it for the quantum form. So for the quantum case, then, as we learned last time, to really get at a quantum system, we need to solve the TISE, the TISE, the time-independent Schrödinger equation, which is this, which is the kinetic energy term, plus the potential energy for the harmonic oscillator, which is this 1/2 m omega squared x squared times psi is equal to E psi. And that gives us the stationary solutions. And from those, we can build up the general solution as a function of space of x and t if we want to. Okay, so how are we going to solve this equation? Well, we're going to use an algebraic approach first. And it's going to use something called ladder operators. Okay, so let's see how this works. So we can rewrite the Schrodinger equation for the harmonic oscillator here in this form: 1 over 2m times the momentum operator squared plus m omega x squared psi is equal to E psi. So we can see this second term, m omega x, if we square it, it's m squared omega squared x squared over 2m, becomes the same as becomes m over 2 omega squared x squared psi. So the second term is pretty clear. And then if you remember that the momentum operator is minus I h bar ddx, then we get, when we square it, we get minus h bar squared ddx. So we get the p squared over 2m takes care of the first term. So this is equivalent here to this equation on the left here. Okay, so now we're going to try to express this left-hand side here with the p squared plus the m omega x squared in terms of these ladder operators called a plus and minus. So a is plus is the raising operator and a minus is the lowering operator. And this is their definition, which looks a little mysterious, but if they turn out to be very convenient. So it's 1 over this square root of 2h bar m omega times a linear combination of the momentum and the position operators. Okay, and we'll see how it's a little mysterious why it is defined this way, but they turn out to have really useful properties, as we'll see in a second. Okay, so to see why we might define them this way, we can see we could take the product of two ladder operators, a minus a plus. And so when we do that, we get 1 over this first factor squared, 1 over 2 h bar m omega times, and we do this, we'll have, when we multiply all this out, we get p squared plus m omega x squared, which is similar to what we have up here. But because these operators, or the p operator doesn't commute with the x, that is, taking p times px is not the same as taking xp. And we'll see why in a second. I'll describe that in a second. We have an extra term, which is minus I over 2h bar times this bracket of x and p. And this bracket of x and p is xp operator minus p operator x, and it's known as the commutator. Okay, so so why might taking first p and then doing p first and then multiplying by x be different from multiplying by x and then operating on that on p? Well, remember, p involves the derivative, so the derivative with respect to x. So if we have x times the first derivative of what's on the right, that's different from taking the derivative of x times something that depends on x, because that'll involve the product rule. So in general, it's not the same to take the derivative with respect to x and multiply by x as it is to first multiply by x and then take the derivative with respect to x. So that's why there's this difference, xp hat minus p hat x is not 0. So what is it and how do we evaluate it? So we evaluate the commutator using a test function. And the result which we'll find, and I'll show you the steps in just a second, is that the commutator is pretty simple. It's just I times h bar. Okay, so if we look at this, we use a test function, a function of x. X and p on that would be xp minus px operating on f. So xp would be minus ih bar ddx of f minus p minus ih bar ddx acting on xf. That's the second term. And then simplifying further, we can pull out the minus ih bar and we have x df dx, which is the first term. Then we have minus the product rule. So it would be x times df dx, and then multiplied by just f, because dx, the derivative of x with respect to x, is 1 times f. So these two terms cancel, the x df dx. We're just left with minus I h bar times minus f, or I h bar times f of x. So and this is an arbitrary test function. So x and p, the commutator of x and p acting on it is just the same as multiplying by I h bar times it. So that gives us the fact that the commutator is I h bar. Okay, so we can use that in this expression up here for the product of the two ladder operators, because that involved the commutator of x and p. So if we plug in I h bar for x and p right here, then we get the h bars cancel. We get I squared, so minus 1, but we have minus that. So we have plus 1/2 here. So this whole term becomes plus 1/2. Then we can take that over to the left side and becomes minus 1/2. And then we can multiply through by h bar omega. And what we'll be left with on this side is the p squared plus m squared m omega x squared over 2m, which is what we're interested in. And that's equal to h bar omega times a minus a plus minus 1/2. Okay, so we've just shown that the energy operator, or the Hamiltonian operator, which we rewrote as 1 over 2m p squared plus m omega x squared, can be written in terms of these new ladder operators as h bar omega times a minus a plus minus 1/2. Okay, so that's a pretty simple form, and we'll see that it's very useful to have it in this form in a little bit. We can also show, you might have been wondering why we took a minus a plus instead of a plus a minus here. Why did we combine it as a minus a plus? So if we combine it as a plus a minus and go through the same operations and the same steps here, we actually get that h can be written as h bar omega times a plus a minus plus 1/2. Okay, so there's just if we use a minus a plus, we get a minus 1/2 here. If we use a plus a minus, we get a plus 1/2 here. Okay, and both of those are used. Probably this last one here is used more often. Okay, so continuing with the algebraic approach. Now we're going to try to find the ground state, the lowest energy state of the harmonic oscillator in the quantum treatment. So it turns out it's possible to prove, and I'm not going to go through the full proof here. You can check the textbook if you want, that if h psi is equal to E psi, so if psi is a stationary state with energy E, then if we operate with h on a plus times psi, we get back a plus times psi times E plus h bar omega. So that means that if we have a function, a state psi, the function a plus psi is also a stationary state, and its energy is E plus h bar omega. So it just, the action of acting on the state by a plus just increases the energy E to E plus h bar omega. And similarly, if we take h acting on a minus on psi, that gives E minus h bar omega acting on a minus psi. So it just decreases the energy of the state by h bar omega. And this is actually the origin of the term ladder operators, okay? Because the A plus, the raising operator, raises the energy E of a state, of a stationary state by h bar omega. And meanwhile, the lowering operator A minus lowers the energy by h bar omega. And that's illustrated here with this very fun illustration. Credit to to our textbook, to Griffith's textbook. It's a very cute illustration. So here's the state psi with energy E. And if we operate with the raising operator A plus, we go up to A plus psi or A plus squared psi or A plus cubed psi, and we raise the energies to E plus h bar omega or plus 2 or plus 3 h bar omega. Meanwhile, if we go downward, we get A minus psi, A minus squared psi. We keep operating with the downward lowering operator, we get E minus h bar omega, E minus 2h bar omega, etc. Okay, so all right, so that's the a crucial property, is that when we so one question is that you might have is, can we continually operate with the lowering operator? Because that's going to keep decreasing the energy each time by h bar omega. Can we keep operating with that indefinitely until we get, a hugely negative energy? And the answer is no. Since the potential of the harmonic oscillator is positive, it turns out that the energy E of a valid stationary state has to be positive, because it contains a positive potential energy, and kinetic energy is by its own nature positive. So, but what if we keep applying the lowering operator A minus? Okay, so if we do that, it turns out that there's a lowest valid state, which has the property A minus times that state, psi 0 is equal to 0. And that's what we mean by the ground state, because psi 0 is a valid state, but if we operate on it with with the lowering operator, we get 0. So we get 0 energy, which is not allowed. So this would be the ground state. And if we plug in the expression for A minus acting on this function, and A minus is 1 over, this is the definition here, with the operator p hat written out, or I p hat written out here, then we get a differential equation for the ground state, stationary state, psi 0 of x. And this is the differential equation here. And this is solved in several steps in the textbook. It turns out that, and then it can also be normalized. The solution can be normalized, and it turns out to be a Gaussian, which is the ground state, the lowest energy state of the harmonic oscillator. So psi 0 of x is some normalization factor, which is this factor out in front, m omega over pi h bar to the 1/4, times the exponential of minus m omega over 2 h bar x squared. So e to the minus x squared is a Gaussian distribution. Looks like a bell curve with maximum probability at the center at x equals 0. Okay, so now we have the ground state wave function, or stationary state. Let's see about finding the excited states. Okay, well, actually first, before we do that, let's find out the energy of the ground state. So since this h bar, so we want the energy E naught to correspond with psi naught, okay? So that means that if we operate with the Hamiltonian on psi naught, we should get back E naught, the energy, times psi naught again. That's the TISE or TISE. So this is the Hamiltonian written in terms of the raising and lowering operators. h bar omega a plus a minus plus 1/2. And we find the ground state energy to be, I'm claiming to be E naught is just equal to 1/2 h bar omega. Okay. And can you see why it's 1/2 h bar omega from this equation on the left here? I'll give you a second to think about it. Think about the property of this lowering operator, a minus, acting on psi 0. What did we said it did? It did to psi 0. Okay, so what it does is when we take this first term and act on psi 0, it actually, remember, a minus times psi 0 is equal to 0. So this whole first term goes to 0, and we have h bar omega over 2 psi 0 is E naught psi 0. So that means h bar omega over 2 is equal to E naught. And we have our ground state energy 1/2 h bar omega. Okay, so now we have the ground state, stationary state, the Gaussian, and we know its energy is 1/2 h bar omega. So having found the ground state, we can use the raising operator to find all the excited states, because that's going to raise the energy to the excited, to the raising operator is called that because it raises the energy of a given state by h bar omega. Okay, so we can write that like this. We can say that the nth state, so n equal 1, 2, 3, etc., we would get by just applying the raising operator n times to the ground state. And then that would give us a state, but there's a normalization factor. Even if we start out with psi 0 normalized, we may have to multiply what we get by some factor to make sure that the psi n we get is actually normalized. And we'll talk about that in just a second. The energy En is equal to n plus 1/2 h bar omega. It starts out as 1/2 h bar omega at E0. And each time we use the raising operator, we add h bar omega to it. So if we do that n times to get psi n of x, we're going to add n h bar omega to the energy. So this is the formula for the energy of the nth state. It also works for the ground state. If we put in 0, it gives 1/2 h bar omega. So it's a general formula for the energy of the nth state of the harmonic oscillator. Okay, so what are these normalization constants an? Well, with a little bit of, well, a fair amount, some involved linear algebra and calculus in our textbook, it turns out you can show that the raising operator acting on psi n gives the square root of n plus 1 times the psi n plus 1. Okay, and similarly, the lowering operator acting on psi n gives the square root of n times psi n minus 1. Okay, we know the raising operator is going to give psi n plus 1, but it actually multiplies, it introduces this factor of the square root of n plus 1 when it does it. Okay, and we can use that to figure out the normalization factors. So how does this work? So, okay, so let's apply this formula here to where n equals 0. So if n equals 0, we have a plus psi 0 is equal to square root of 0 plus 1, or square root of 1 times psi of 0 plus 1, or psi 1. So psi 1 would be 1 over the square root of 1 times a plus psi 0, which is what we have here. Applying it for for n equal 1, we'd have n equal 1. This would be psi 2. This would be 1 plus 1 is square root of 2. And that would be psi 2 would be equal to 1 over the square root of 2 times a plus psi 1. And this first, you can maybe start to see the pattern for psi, for n equal 2, we have psi 3 here. We have square root of 3 because it's 2 plus 1. We divide by square root of 3 and we get a plus psi 2 over square root of 3 is equal to psi 3. Okay, so in general, each time we raise the, each time we apply the raising operator, we get a factor of square root of 1 first, square root of 2 second, square root of 3, square root of 4, etc. So we keep getting square root of 1, 2, 3. So if we applied, if we started with psi 0 and applied a plus 3 times, we would get first the square root of 1, and then that would give us psi 1. Then we'd apply that again and get the square root of 2. And then we'd apply it again to psi 2 and get the square root of 3 to get psi 3. So we would get square root of 1 over the square root of 1 times 2 times 3 times a plus cubed psi 0. So this leads to the general formula, which is that psi n would be 1 over the square root of n factorial. Remember, n factorial is n times n minus 1 times n minus 2 down to 1. So in this case, for psi 3, it would be 3 factorial would be 3 times 2 times 1 times the raising operator to the nth power times psi 0. So that's a normalized wave function there. So looking back at what we had before, this an, comparing this equation up here to this equation here, we have an is 1 over the square root of n factorial. So the normalization constant then would be an equal 1 over the square root of n factorial. Okay, great. So we've done covered a fair amount of ground. We looked at the classical harmonic oscillator. We saw that it was very useful, that it applies to different situations, that anytime you have a minimum, you can approximate it very closely by a harmonic oscillator close to the minimum. So it's very widely useful. We looked at the definition of raising and lowering operators, how we could write the energy operator for the quantum system in terms of them. We found the ground state for the harmonic oscillator using the properties of these, specifically the lowering operator. Then we found the energy of the ground state, and then we constructed the excited state by using the raising operator. So we've got a full set of states. We know the energies of the states, and we know the function, the actual stationary state for the ground state. And in principle, we could use the raising operator to get any excited state we wanted to using this formula here. It would involve multiplication and taking some derivatives of the ground state wave function. Okay. All right, so next time we'll take another look at the quantum harmonic oscillator using an an analytical approach. So another approach to getting these wave functions or to these stationary states, which comes to the same point, but is different from using these the algebraic approach with the raising and lowering operators. All right, thank you for your attention, and I will see you in class.